Okay, so in the past we have looked at the chain rule, we have looked at the fully connected layer, we have looked at the forward prop and the backward prop for the fully connected layer. And now we need to know just two more things before we can write up our own PyTorch equivalent. One is an activation function, and we'll talk about in this session why do we need it. And two is the loss function. And what we will code up first is ReLU because it's simple and it actually works, and the cross entropy loss function. So let's talk about why do we need these nonlinearities? Why do we need these activation functions? So the simple answer is, think about what happens when you have, say, multiple fully connected layers. Yeah, let's say you have your input X and this goes into, let's say, the first layer. It has some weights W1 and we call it, let's say, layer 1, and then it gives us, let's say, the activations here, and then we put it into, let's say, another layer W2 weights, and layer 2 it gives us, let's say, A2, and let's say we put this into another one which gives us the final output. Let's say we call it layer 3. So this is our layer 3 and it gives us the output, and we have no activation layers in the middle. Now if you think about it, if you write it mathematically, you will see that your A1 is nothing but W1x. Similarly, your A2 is nothing but W2A1, and lastly your output is nothing but W3A2. Now you can also write your output as, let's say, so we have A2, so W3, and then we are replacing this A2 with this expression here which is W2A1, and then let's replace A1 with this expression here, so W2 and then W1x. And now we can argue and say, okay, why do we need these three matrices? Why not learn just one? Right? So it collapses when you have multiple linear layers one after another, it collapses to just one big linear layer, right? So you can just instead learn some another W which will do the same task. So this is the reason why we need nonlinearities, and I'll show it with a very easy to follow example later on within this session in the next 10 minutes. But remember, why do we need nonlinearities? Because otherwise if you just have these linear layers, everything just becomes linear and you're not able to do these complex non-linear so-called decision boundaries. Now let's talk about the old school, say, activation functions. The sigmoid happened to be probably the oldest one, inspired from the mind, and what sigmoid does it squishes. So always your x-axis, this one, is your input. Yeah, and no matter, so your input, the domain is -infinity to infinity, meaning your input can be anywhere from -infinity to +infinity, and then your activation layer, your nonlinearity, squishes it between 0 and 1, right? So it's always positive. So look what it is doing. If it's -infinity, anywhere between anything less than -5, it almost becomes 0, and anything plus more than, say, +5, even then it becomes just 1, right? So it is, in some sense, we call it in this region and this region, we call it to be saturated. So it's saturated, meaning it's either 0 or it's 1. And whenever an activation function is saturated, the gradients, the slope, you can clearly see, is 0. So any gradients that are coming in, it will kill it. So it will lead to this so-called vanishing gradient problem, which again we'll talk about in a minute. So what does this function look like? It's denoted by sigma. Sigma is a special symbol that we use for the sigmoid function. It has this mathematical expression where x is your input. So it's 1 upon 1 plus e to the power minus x. If you plot it, you see that you get this kind of a curve, and you can do this even just on the Google search bar. You say, maybe we'll do it in a bit. So you just say y equals 1 upon 1 plus e power minus x, and you will get this curve. Now what does it do? It squashes numbers in the range 0 to 1. And it's historically popular because they have this nice interpretation as the saturating firing range of a biological neuron, of an animal neuron, meaning this is how, the saturation of a actual neuron happens. But it has a few problems, and so we don't use it today. One, saturated neurons kill the gradients, like I just discussed. So anything, so if your x was in this region, or so if it was in this region or this region, your gradients are 0, and that is bad because then you're not able to learn. Your sigmoid outputs are not 0 centered. We'll talk about later when we talk about weight initialization, why is it important. 0 centered meaning it is between 0 and 1. It's not between, say, -1 and 1. And this is why, there are issues when your weights are initialized around 0. And we'll talk about this when we talk about weight initialization. And finally, the exponential function can be a little bit expensive to compute, but this, in my opinion, is not such a big problem. Then what Jan did in 1991, especially because of this non-zeroed, so he tried to kind of fix this issue because they were not centered around 0. He said, okay, let's try and fix this issue. And what did he do? He said, okay, instead of sigmoid, let's just use tan h, and tan h happens to be this function, e power x minus e power minus x upon e power x plus e power minus x, right? So when you do this, you get tan h. The properties are similar. It's like a sigmoid. It has, it saturates. Anything here is saturated and the gradients are still 0, but it's at least 0 centered, meaning we have -1 as the minimum and +1 as the maximum. So it squashes numbers in the range of -1 to +1. It's 0 centered, it is nice, this is what he set out to fix, but it still kills these gradients when saturated, right? So in this area that we discussed, it still kills the gradients, and I don't like that. Then this, so by the way, we will actually use tan h when we do GANs, and we'll see why we use tan h. It's actually a form of just normalizing it. But in practice, in real life, we use ReLUs, and we like ReLUs, and this was invented by Nair and Hinton in 2010. So a little bit more recent when in the grand scheme of things, especially since since these kind of things came up in the 90s, so 20 years later almost. And ReLU, what it does, ReLU is a very simple function. ReLU is max of 0 comma x. Now max of 0 comma x can sound fancy, but the way I want you to remember is that ReLU is just the same, so let's say your f of x or your y is x. What is your function? You have done this in high school, right? So your function y equal to x is this. So as long as your x, remember x is always your input, right? So this is your x axis and this is your input. So as long as your x is in the positive direction, as long as your x is positive, your y is the same as x. But as soon as x is negative, the output is 0. Yeah, so that is all that ReLU is. So what it is saying, and this is a nice way to write it. If you want to write it mathematically, concisely, you're saying it's max of 0 comma x, meaning if your x is greater than 0, then it is x, but if your x is less than 0, then it is 0. Yeah, so that is all it is. So whenever, so your y equal to x is just a straight line, that is just copying your input to the output, but instead of copying it completely, we are saying, okay, we are only copying it if it is positive, and if it's negative, we are making it 0. Now, what are the advantages of this, this nonlinearity? One, it does not saturate in the positive region. It's computationally very efficient, and it converges much faster. So we have found this empirically, that in practice it converges much faster than your sigmoid or tan h. What are still the issues? It's not 0 centered, and there is a small annoyance that what happens when the gradient is less than 0. Well, when x is less than 0, what happens to the gradient? Well, the gradient is 0. Right, because here it's again flat. So it can sometimes lead to some issues, and we'll discuss this later, but for now we can just ignore it. So now I want us to look at this in more detail. And before we do that, I want you to also look at, let's say, something called as leaky ReLU. And leaky ReLU is used for training, let's say, GANs. So when we actually write GANs a few weeks later, we will see we use leaky ReLU, and we'll also try using ReLU, but it doesn't work as well and it's more difficult to train. Why? Because gradient flow in GANs is even harder, because there's a very sparse signal and the gradients are very weak. And what happens with ReLU is that in the negative region it completely kills the gradient, but with leaky ReLU what it does, it passes at least a little bit. So what is leaky ReLU? It says, okay, in the positive region I'm always X, which is just copying it, but in the negative region I am, let's say, 0.01x, meaning I'm passing a little bit of the gradient. I'm passing 0.01 part of the gradient also in the negative regime. What are the advantages? Well, it does not saturate, it's computationally very efficient, and it converges much faster than sigmoid tan H in practice, again 6x, and it will not die, meaning it doesn't completely die, right? The gradients might still become very less, but it doesn't die, and this is actually a big achievement for especially for training, difficult to train models such as GANs. And this was invented by, published by Mas et al. In 2013. Then people took it a step further. So Hay et al. Took it a step further, where he said, okay, instead of like just fixing this 0.01, why don't we make it learn? And we actually back propagate it. We differentiate the loss with respect to this parameter, and then we also take a step in this direction, right? So what we say is, alpha is equal to your previous alpha minus, let's say, some lambda times learning rate times derivative of loss with respect to this alpha. So we actually back propagate into this alpha and train it. So instead of hard coding it, we say, okay, let's make it a trainable parameter and let's just back prop into alpha and train it. It was also, so Cumming Hay came up with this in 2015, and the advantage is the same as leaky ReLU, just that it's parameterized and maybe it can learn a better parameter, but I've not seen people use this in practice too much. And it's called p-ReLU. And then the list goes on and on. There is LU. LU is essentially, this curve that you see, the blue one. And the advantage of this is, so this is your 0, right? So this is your x-axis, and your purple one, which is 0 or this. So here everything is the same, right? They're all overlapping each other in the positive region. In the negative region is where they differ. So this is your leaky ReLU. This is the so-called S ReLU, and this is your LU. So the advantage is that it is smoother, it has all the benefits of ReLU, it does not die, and it's closer to the zero mean of outputs, and we'll talk about the zero mean when we talk about weight initialization. And this also came up by Clevert et al. They published it in 2015. And then there is like a lot of additional work, including, let's say, this paper of empirical evaluation of rectified activations in convolutional networks, and it goes on. One interesting thing I want us to see is this thing called as glue, right? So this is the so-called so this is another. So this is your the so-called swish activation function, swiglu. So the swiglu is another activation function. So we have to cut here, Vishal. I hope you're watching this. So we will cut here, and then I'll talk about this another interesting thing. Vishal. So let's look at something again interesting. So because these activation functions keep going on. So this is, for example, swiglu, and this came up in 2020 by Noam at Google, and he talks about things that, and these are actually used in transformers, in diffusion models. We will see when we look at some of them. But something very interesting about this paper that I like is, look at what he says in the end. He says, so we offer no explanation as to why these architectures seem to work. We attribute their success as all else to divine benevolence. So I think this is funny, and this is sometimes difficult to explain why this works other than doing it empirically. Now, in TLDR, you should remember that we want to use ReLU, and this is what we will code up. But we have to be careful with our learning rates. We can try leaky ReLU, LU. You can also maybe try tanh, but don't expect much and don't use sigmoid. Yeah, and it's an active research area. There's like still a lot of research being published on activation functions, but I think we have covered the most important ones, the ReLU, the leaky ReLU, the sui glue, and we will look at specialized activation functions when we do these, you know, more interesting, or let's say the more modern models, right? If we look at flux, if we look at, you know, so when we look at those kind of diffusion models or some transformer based models, we will look at the activation functions that we use, and then we will briefly discuss it at that point. My goal here is to get us up to speed with ReLU, because once we have ReLU, then the only thing we need is the cross entropy loss function, and then we can code up our PyTorch equivalent for our this week's assignment.